Good morning, sunshines. We're going to talk about dilations. So, a dilation is our last transformation that we're going to talk about. A, it is a transformation that produces an image that is the same shape as the original, but not necessarily the same size. So, the three transformations that we talked about already translations, reflections, and rotations maintain the size of your shape, but a dilation is going to be the only transformation that does not do that. So, when you do a dilation, it is similar to the original figure. That mean similar is just the math way of saying same shape, but not necessarily the same size. And dilations are centered around the origin unless otherwise stated. So, for dilations, the key thing that we care about is the scale factor. That's you can write it as a fraction, the image length over the pre-image length. So remember that's your after over your before, which is a little bit counterintuitive. And when you have a fraction that compares two values, that's called a ratio. So your scale factor, if it's bigger than 1, that means so when a fraction is greater than 1, that means the numerator, the top of it, is bigger. So that means your after figure, your image, is bigger than your pre-image. So it gets larger. So we call that kind of dilation and enlargement. And then opposite direction, if it's between 0 and 1, that means your before, your pre-image is the bigger one. And so it got smaller. And so we call that kind of dilation a reduction. Now, it's important to pay attention to those boundaries. Greater than 1, but then the other one isn't less than 1, it isn't equal to 1, it's between 0 and 1, not inclusive. You cannot have a dilation of 0 because that would just make your shape go away and it wouldn't exist anymore. If you have a dilation of 1, that's your identity dilation. It means you didn't do anything. It's like rotating by 0 degrees or translating by 0 boxes. A scale factor of 1 would just be nothing. Now, if it's a negative number, what happens is that then you've effectively rotated it 180 degrees at the same time. So since that rotation would be a separate thing, we don't count it. So you can't have a negative scale factor, but you could have a negative multiplier where it's just basically a compound transformation. So we usually use the letter F to represent our scale factor, and your scale factor is actually a multiplier. So if my scale factor is 3, that means I'm actually just going to multiply the coordinates by 3. So my rule is going to be xy maps on 2, 3 times x, 3 times y. So if I have a triangle that has these 3 points as its vertices, the image is going to be, with a scale factor is 4, the image is going to be these coordinates multiplied by 4. So my algebraic rule is xy maps onto 4x times 4y. So for each coordinate, I plug that coordinate into the rule. So if my x coordinate is 0, a prime is going to be 4 times 0, which is 0. And then 4 times 2 is going to be 8. And then I do the same thing for my others. 4 times 4 is 16. 16. 4 times -1 is -4. Oops. And 4 times 4 is 16. So this is our concept. And then now we're going to try this on an actual graph. So we have quadrilateral PQRS with vertices -2, 4, 4, 4, 4, -2, and -4, 4. So we're going to dilate it by a scale factor of 1/2. So my shorthand notation is D 1/2. And then my algebraic rule is xy maps on to 1/2 times x, 1/2 times y. So for point P, I'm going to multiply those coordinates by 1/2. So half of -2 is -1, half of 4 is 2, and I do the same thing to the rest of my coordinates. And then I graph them. So when I graph them, I'm halfway because my scale factor is 1/2. I'm half the distance from the origin. It's always a good idea when you're doing transformations to switch colors so that your image is a different color from your pre-image. It makes it a little easier to keep track, especially as you're writing out your work to help color code things. So when you go do comparisons, you're not forgetting which one's which. For a shape like this, it doesn't matter as much because it's completely contained. But when you have overlaps, it can get really confusing to try and find which points belong to which figure. So now I want to do a little bit uh, of analysis. So we want to show that the quadrilaterals are similar by comparing the ratios of the lengths. We want to show a couple different sides to show that they have the same scale factor. So the original figure PQ, this length here is 4. This, not 4. This length here is 6. And this length here is 6. With horizontal and vertical lines, you can just count the boxes out. But for a diagonal line like this, you're going to need the distance formula. When you set up your distance formula, remember not to lose that square root. The whole thing is underneath a square root. So the distance formula is set up with using actual coordinates, but once you do that first step where you find the difference of the y's and the difference of the x's, remember that you get the rise and the run. So on a graph like this, you could skip to this step by just counting out. This is -2 and this is 8. Since we're squaring them, the signs don't really matter. I would probably have counted it going this way. I would have done it's up to over 8 and just used the positive values because you're finding distance, so you only care about the positive. But the distance formula is really just the Pythagorean theorem. So when you solve it out, you get the square root of 68, which in simplest radical form is 2 root 17. And so for a segment SP, I don't have to do the point calculations again because I can see I'm dealing with the same values. I'm just dealing with that same 8 and 2. So it's going to be 2 root 17 again. And then you do the same thing for the smaller one. So the horizontal and vertical are each 3. And then the diagonal ones, this time it's a rise of 1, run of -1, run of 4, -4. And this one's 4, 1. So again, the same numbers. So the square root of 1 squared plus 4 squared is 1 plus 16, so it's the square root of 17. So when I set up my ratio, so my ratio is image over pre-image. So I'm going to get I've got 3, 3, root 17, and root 17 over 6, 6, 2 root 17, 2 root 17. So when I simplify those fractions, 3 over 6 is 1 half, 1 half. The square root of 17 is going to cancel out and leave me with half. So I got a half every time, which is the scale factor that I started with, and so that's the answer that I should have. So the lengths get multiplied by the scale factor, the distances get multiplied by the scale factor, everything gets multiplied by the scale factor. Except what do you notice about the angles? Did the angles get multiplied by the scale factor? So let's look at angle Q because that's the easiest one. Angle Q is the intersection of a horizontal and a perpendicular line. So we know that that's a right angle because horizontal and perpendicular, horizontal and vertical are perpendicular. So this is a right angle and this is a right angle. So the angle measures actually stay the same. So just be careful about that. Distances are changing when we're being multiplied by the scale factor. Lengths are being multiplied by the scale factor, but angle measures always stay the same, even when you make the figure bigger or smaller. And so there's a few more examples in the packet, but I'm going to go over them in a separate video.